So, let us now deal with time reversal in quantum mechanics. So, you have got the uncertainty principle for position and momentum. You have canonically conjugate variables in which time appears along with energy. The operator for energy is the Hamiltonian, but there is no operator for time. And the reason for this is very complex, but if you look at the difference between classical phenomena and quantum phenomena are very subtle. If you look at even the spectrum of the hydrogen atom, you have got a continuum above the Rydberg series limit. Below the Rydberg series limit, you have got discrete energy states which converge to the Rydberg limit, but then there is a lower bound. There is nothing below 1s. There is a bound. As a matter of fact, you know that in earlier days of quantum mechanics and spectroscopy, this was called as the K shell. If you follow the terminology in X-ray spectroscopy, the 1s is the K shell. Why K? It could be any other alphabet. It was K because of the 26 alphabets, K comes almost in the middle. It is either 12th or 13th or something like that. Because people did not know that maybe there is something beneath it. So, they took the middle letter, and this is written in a nice article by Mitio Inokoti. He has written about this in a very nice article. I might have that paper somewhere. So, this was the K shell, but then we know that it is the lowest one. There is absolutely nothing below that. And it is because of this that the energies time relationships are different from QP, because Q and P there are no such limits. P goes all the way from, in a one dimensional problem, from minus infinity to plus infinity. X also goes from minus infinity to plus infinity, but that is not the case with time energy. So, there is a lower bound, and as a result of this, time is treated as a parameter in quantum mechanics. There is no operator which is self adjoint of which it is an eigenvalue. So, the operator for time does not exist, and time reversal is not the same as the inverse of time evolution. So, let us ask ourselves, what can time reversal mean in quantum mechanics? So, we begin with what we understand of time evolution, that you have a state vector alpha, its time evolution operator is 1 minus I h delta t in units of h cross, and you get a new state vector, right. This represents time evolution, and now we look for what time reversal ought to mean. Wigner preferred the term motion reversal rather than time reversal, but the two terms are used mostly synonymously in common literature. So, now we are examining what can theta alpha mean to us. Theta is what we will use the symbol theta to represent the time reversal operator, the operator for time reversal symmetry. So, when this operates on alpha, you will get a new state, and what do we expect of those states? What we do expect is the following: the time evolution of a time reverse state is what we would represent by this. Theta alpha is the time reverse state. Time evolution we are already comfortable with, it is 1 minus I h t I h delta t by h cross. So, this is what we mean by time evolution of a time reverse state, and we expect that this would be the same as the time reversal of a time evolved state through negative time. That is what one would expect. So, this is our heuristic expectation of what theta ought to mean in quantum mechanics. So, this is the criterion, that this is what we expect, and if we can find what is theta such that this condition is satisfied, or what will be its properties, then we have the time operator for time reversal, and we do not expect it to be the same as the operator for time evolution through minus delta t. That is the inverse of the time evolution operator, it is not the time reversal operator. That inversal is equal to adjoint, it is a unitary operator, all that is good, but we are now talking about a different matter altogether. So, this is our expectation, and since alpha is an arbitrary state, the operator which operates on it must be equal on both sides of the equation. So, theta must satisfy this property. So, we will examine this property in some details now on the next slide. So, this is the property we want theta to satisfy. Let us spell it out. Theta, the first term on the left hand side will give 1 times theta, it will give theta itself. On the right hand side, the first term is theta times 1, which will again give theta, right. So, we will write it out term by term, and this is what we get. But we preserve the order in which the symbols are written, because we do not know what commutes with what and what does not. Okay. So, we do it carefully. So, here we are good with this, everybody?
Motion reversal should also act for the same amount of time that the time property lasts. Is that a condition?
Yes, yes, that you are looking for such an operator which will neutralize the effect of time evolution through that. It will, you will see that it does turn out to be that. So, we have this relation which presents itself as a condition on theta. Now, we cancel the theta on the two sides, we cancel the minus sign on the two sides. Okay. From what is left, we cancel the h cross in the denominator on the two sides. What are we left with? I h theta delta t equal to theta I h minus delta t. We take off delta t as well, we could have done it in the previous step too. And now look at the minus sign, it is carefully preserved and retained over here, that minus I h theta must be equal to minus theta I h, and we have not played with the positioning of any of these symbols, including the square root of minus 1 I which appears there. Okay, we have not tampered with it. Very often when we do complex analysis, we would not bother about it, but this is what we expect. And now let us ask, if theta were a linear operator, if theta were a linear operator, then theta I would be equal to I theta. Okay. So, we were talking about the linear and antilinear character of these operators just a little while ago, and that will become very clear now. So, theta I would be I theta if we use the property of linear operators. What would it do to the right hand side? Right hand side will become minus I theta h. The left hand side is I h theta, and this means that h theta will be equal to minus theta h. That is what we will be led to if we assume that it is a linear operator. So, let us see if this works for us. Let us apply the operators on both sides of this equation to a state vector. So, this is like a condition that we are examining. We know that if this is satisfied, if theta is a linear, then this is what we would get, and if h theta is equal to minus of theta h, then the operation on an arbitrary ket by either the left hand side must be exactly the same as the operation by the right hand side. So, I use an energy eigenket and operate on this by the left hand side's h theta and also by minus theta h of the right hand side. But En is an energy eigenket, so it is En right, and you find that theta En, which is again a state vector, is an eigenket of the Hamiltonian, but belonging to a negative energy. Now, what would it mean for energy states of a free particle? A free particle is always in a positive energy state. Okay, you are not getting an anti-particle out of it. All right, so this cannot work. So, our conclusion is that this cannot be a linear operator. So, on the next slide we ask if it is if it is an antilinear operator. So, now having concluded that it is not a linear operator, we ask if it is, so this is our overall expectation. We now examine the possibility that theta is an antilinear operator, and if it is an antilinear operator, then theta I would be minus I theta, not I theta. So, there would be a complex conjugation. So, this is the antilinearity which is taken advantage of over here. You were asking about it. So, the antilinear property bails us out, and what it leads us to is that theta En is an eigenstate of H belonging to the same eigenvalue with the same sign, which is all right, which works just fine for us. So, theta must be an anti-unitary operator and not a unitary operator. So, the time reversal operator is an antilinear, anti-unitary operator. It is important to recognize that theta I is equal to minus of I theta, and when you talk about t going to minus t, then there is a complex conjugation which is getting involved. You will see it more clearly possibly on the next slide.
So it seems as if theta preserves the energy of a system. So is this because we are considering stationary states?
It preserves
The energy of the system, even when we add theta, the energy still remains En for the Hamiltonian.
Yeah, in this case, right.
So is it because only we are considering stationary states, because En is a stationary state?
Yeah, physical states of a system means we work with stationary states, but when the states is not stationary, then there are other consequences which are not involved over here, and what will happen is their superposition, the probability densities may not be time may be time dependent. That might reflect transition from some initial state to another state and so on, but that transition is brought about by completely different interaction. There has to be some physical interaction which is involved in bringing out that transition, which will change the probability densities. Okay, here time reversal symmetry is not bringing out any such transition in those states. Okay, it is only telling us what is the meaning of a time reversal symmetry. Okay, symmetry in the sense that, okay, you have got an operation which leaves the law of nature invariant. You are not talking about interactions which are bringing out changes in the state of a system from one to another, in which the probability densities are changing. That may be due to a transition. That might involve some coupling between the system and a radiation field or something else. So, that is a different experiment altogether. So, these are some properties, you can work this out for yourself. This is good homework problem for you. R remains invariant under time reversal. Momentum becomes minus p under time reversal. Okay. So, R commutes with time reversal operator, p momentum anti-commutes with the time reversal operator, and for commonly encountered operators you can build these relationships. Angular momentum again anti-commutes, it does not commute. You can compare these properties also with parity. So, parity and time reversal are discrete operations. So, we are talking about a little while ago we were talking about the time reversals through the same time interval delta t. It is the same with the difference that it is in one step. Okay. In the case of time evolution, you can talk about a inverse of this in various intermediate steps. You can get to tomorrow from today by going through the afternoon and then the evening and then the night and then the next morning. You can go backward in time, which is the inverse of the time evolution, by going through the last night and the previous evening and the previous afternoon and the previous morning. You can go through this continuously, but in the time reversal operator there is a discrete jump. You do not go through intermediate times, you go from here to there in one step. It is just like mirror reflection. So, you have got a mirror, you are over here and you see the image over here, but you can come here by going here, or now this is rotation, but in a reflection there is nothing in between, you go from here to there, and it is because of this that the left goes to right and the right goes to left, but the top does not go to the bottom and the bottom does not go to the top. Okay, that is a different symmetry. So, it is not laws of reflection, there is more to it than just the laws of reflection. Laws of reflection are of course there, but they do not explain why the top does not go to the bottom. If you change the axis, of course top goes to the bottom, but then the left will not go to the right, and this is because the left right belongs to a symmetry which is represented by for parity you need larger group, whereas in rotations the determinant of the transformation must be +1, whereas for parity it is -1. So, it is not just O3, but it is SO3, the special orthogonal group SO3. So, these three symmetries are discrete symmetries: parity, which goes from this space to the image space in one jump; time reversal, which goes from one instant of time to minus that with reference to a 0 in one step, you are not going through anything in between, it is a discrete symmetry. And the third discrete symmetry is the charge conjugation, that a particle goes to the antiparticle, and it is this symmetry together, which is preserved in the CPT theorem, as it is called. I like to call it as PCT theorem because it rhymes with my initials. So, it is the PCT theorem, and it is a cornerstone of the standard model of physics. And Pauli worked on this, and so any one of these symmetries can be broken, but then also some of the other, and together it has to be satisfied. So that's a different topic altogether. So these are certain properties of parity and theta, which are the two discrete symmetries which are of interest to us in this domain of physics. And if you look at the Schrodinger equation, now put t equal to minus t, okay, then you get minus I cross del psi by del t. The argument of psi goes from plus t to minus t. Now, by writing this, do you have a Schrodinger equation? In the second row, it is not even a Schrodinger equation, right? It is not a Schrodinger equation. But if you now do complex conjugation, let minus I go to plus I, psi go to psi star. So you do complex conjugation along with t going to minus t. Then what you have, you can write psi star r of minus t as some function of r and t, and you have essentially preserved the form of the Schrodinger equation. So for time reversal, you need t going to minus t together with complex conjugation, and there is no such analog in classical physics. So classical physics time reversal only means t going to minus t. There is nothing like complex conjugate phenomena, because classical state of a system is represented by real dynamical variables q and p, whereas state vector resides in a complex vector space. So this is fine, and t going to minus t and complex conjugation must go together. We have various, I mentioned earlier also that the boundary conditions and choice of normalization go together. If you have a one dimensional problem, you have got an incident particle in region 1, region 2, region 3. These are the usual problems that we do in the first course in quantum mechanics. And if you are using this to represent a one dimensional collision in which an electron is incident from the left, then you have this red arrow which represents an electron incident from the left. Why is it moving from left to right? Because there is an implicit time dependence e to the minus I omega t, and the phase is given by kx minus omega t, and a surface of constant phase will have kx minus omega t to be constant, k dx minus omega dt must be 0, and k x over t must be a positive quantity, which is why it is moving from left to right. Without all that, it is not even moving. So there is this time dependence which you must always keep at the back of your mind. So this is your incident wave from left to right, and then it may get backscattered, or it may tunnel through, or if it has energy, sufficient energy, it may hop over. If it has more energy than the height of the barrier, even then it can get reflected, okay. That is called as over the barrier tunneling, which is not often discussed. We normally talk about under the barrier tunneling when it does not have enough energy and it can still penetrate, but if it has sufficient energy, it does not mean that it will go through, it can get reflected. So there are two possibilities at the end of this scattering, represented by this arrow, which is b e to the minus I k x, and this term which guarantees that G must be 0, because there is nothing else to correspond to that motion. So, you can represent these boundary conditions by the choice of these coefficients, and it is these coefficients which determine their size, the norm. So, the norm and the boundary conditions go together. And if we talk about photoionization as opposed to collision, then you have an electron which is born when photoionization takes place, and that is the escape direction. Where was it before photoionization took place? It was nowhere. And you can only pretend it by these dashed blue lines. You can pretend that the flux on these two sides cancel each other exactly, convincing us that it did not exist. But if you use such boundary conditions in your quantum mechanical equation, and now you have F equal to 0, okay. So, the photoionization boundary condition is represented by F equal to 0, whereas the collision boundary condition is indicated by G equal to 0, and this is the choice that you can make.
So, the whole solid blue arrow could be also to the right. It's just a convention that we are taking. The solid blue arrow could also be taken to be to the right. This is the escaping electron. Right now, electron escapes to the left.
Yeah.
It could also be.
Yeah, of course, of course, of course. So, even in the collision one, I assume that it is impinging on the target from the left, but it could also impinge from the right. So, wherever it impinges from, the result will be different, but it will have both the possibilities in collision. In photoionization, there is only one possibility, that the electron escapes either to the left or to the right. It cannot go in both ways. If photoionization has taken place, you are going to see it in a detector which is here. If the photoelectron has escaped in this direction. If it has not, you will not see in this detector, you will see it in this one. Okay. So, I consider photoionization in which the electron escapes to the left, and this I represent by the boundary condition F going to 0, and outgoing waves in the final state are defined over here, and in photoionization the ingoing waves in the initial state cancel each other. So, in a certain sense, if you look at the blue arrows and the red arrows, they are like motion reversal. Okay? And you can represent this, the same quantum mechanics, you are solving the same one dimensional problem, and this is very nicely done in the book by Fano and Rao, Theory of Atomic Collisions and Spectra, but that was the inspiration for the elective course that we developed here at IIT Madras, Theory of Atomic Collisions and Spectroscopy. The title also is almost the same as that of Fano and Rao's book, and very nicely discussed in Fano and Rao's book, which is where I learnt this from. So, now you have the time reversal of collision giving rise to photoionization in a one dimensional problem in the upper figure, and in the lower figure you have the same in regular 3-dimensional scattering, where the solutions will look a little more involved, the scattering amplitude comes into the picture, the Faxon-Holzmark expansions and so on, partial wave analysis, all that will come into the picture when we work with 3-dimensional models, which is what we will do either now or in the next class. I think next class. I want to end this class by pointing out to you as to what happens to the law of nature under time reversal. And the uncertainty principle that position and momentum do not commute, that it is equal to I h cross delta I j, is the law of nature. Okay, it represents the law of nature. Newton's, Hamilton's equations do not represent the law of nature, this one does. And we ask what happens to this law under time reversal. So, what is in red is the law of nature, what is in black is what happens to this law under time reversal. Okay. So, let us examine this. We already know how position and momentum respond to time reversal, we just did that a little while ago. So, we expand the commutator Rp minus Pr. I have students who struggle with this Rp because both are vectors with no dot or not a cross in between and they do not know how to handle it, because it is not the dot product of two vectors, it is not the cross product of two vectors, it is actually a dyadic. And how to write the uncertainty principle Rp equal to I h cross delta, there is a unit dyadic on the right hand side which is actually sitting there but not explicitly written, and I think it is a good exercise to write it explicitly and then figure out how these dyadics really work. So, if you have not done that exercise, I strongly encourage you to do that, otherwise it is very embarrassing that you have difficulty with the basic uncertainty principle. So, I assume that you are familiar with how to interpret these terms. So, we have expanded the commutator Rp minus Pr. I now have write the theta and theta dagger on bracketing these two terms separately. Let us do it further and let us remember that this is an anti-unitary operator. So, on the right hand side you will pick up a minus sign, okay. You will pick up a minus sign and essentially you will get the original uncertainty principle just with a change of sign, which is good. It means that what we believe is the law of nature represented by the uncertainty principle, and we know that the time reversal symmetry is a good symmetry in nature. Of course, when you deal with certain phenomena, especially in particle physics, you have to be careful about it. It has got interesting consequences because of the PCT theorem. There are possibilities that an electron may have a permanent dipole moment because of properties of these symmetries and so on. So, that it is a property of, it is a topic of great interest in particle physics, but also in atomic physics, because you can look at some of these properties by doing atomic experiments which are much cheaper than doing high energy physics, and you may get the same physics out of it. So, parity violation of course has been seen in atomic experiments, and when which is coming from the Glashow theorem, the Glashow of the Salam work. Because of the electroweak unification, the weak interaction and the electromagnetic interactions are unified. So, if parity is violated in over here in weak interaction, in beta decay we know that it is violated in the experiments of Yang and Lee, and experiments done by Madame Wu, theoretical analysis done by Yang and Li. These Chinese names, they sound so similar to each other. So anyhow, this is atomic physics, and we are not getting into aspects of particle physics. Our domain of discussion is very restricted, and when we come back after lunch, I will use this time reversal symmetry operator to represent solutions of photoionization from the solutions of quantum collisions. And not only that, we take it one step beyond it, that in quantum collisions we have a time delay of the scattered particle, which is the Wigner time delay or the Smith time delay. We then expect a time delay to be measurable in photoionization because of the symmetry. So, we will discuss it in the last class, which will be after lunch, after a light lunch. If there is any question, we can take it.
So, we're earlier talking about how we can't associate an operator with the time variable. Generally, when we talk about operators, you ask for eigenvalues that represent the state of a system. How does time come into this picture of saying something about the system?
It does not. There is time does not show up as an eigenvalue of an operator. It is therefore treated only as a parameter in quantum mechanics, not an eigenvalue of a measurable physical quantity. Eigenvalues of measurable physical quantities, eigenvalues of what? Those are eigenvalues of operators which are self-adjoint operators if they are physically measurable. Time does not emerge as the eigenvalue of a Hermitian operator. There is no Hermitian operator. I think in the early days of quantum mechanics there was an attempt to find an operator for quantum mechanics. And I think even now there are some people who are looking for some related mathematics. I am not completely up to date on that, but I know that there is some effort in that direction. But in mainstream quantum mechanics, there is no formal operator for time.
But if time comes out to be an eigenvalue, what does it represent of the system? Like position represents where the particle is.
But I do not even know if it comes out as an eigenvalue of an operator. In fact, the conclusion of mainstream quantum mechanics is that it does not. So, time is a very mysterious thing. I think was it Einstein who said that nobody knows what time is, and for many reasons. What is present for one is future for someone else, is past for somebody else. So, relativity has additional consequences which deepen the mystery, but quantum mechanics has its own reasons to make it mysterious, which are different from the reasons of relativity. So, conventional quantum mechanics does not look at time as an eigenvalue of any operator. It proceeds by saying that time is only a parameter with reference to which other quantities can be defined. There is no operator for time, and you work with it as an argument of a function. Psi is a function of t, but there is no operator for t. But the interesting conclusion that we arrived at in the previous class is remarkable, especially in this context, that there is no operator for time, but using Smith's analysis of the time delay, we showed that there is an operator for time delay. For time delay, there is an operator we also showed that it is a Hermitian operator and satisfies the necessary condition for that property to be physically observable. Now, that is of great relevance to our interest in measuring photoionization time delay. Okay, thank you very much.